In the second part of our term project, we introduce you to the optimization of a linear function under the constraint of a Cobb-Douglas function using Newton's method. After a busy semester as a TA, teaching Math 23A, Joe is looking forward to spending the evening with beer and pizza. His Cobb-Douglas utility function is given by the following expression, where x denotes beer and y denotes pizza. His experience has shown that he has a perfect evening at the utility level of 10. So, just the Cobb-Douglas function has the graph that looks like this, again using the library Plotly. We have beer and pizza on the x and y axis and utility and cost on the z axis, respectively. So we add at z equals 10 the utility level that Joe wants to aim at and get the following orange plane. Since Joe wants to spend his vacation on pricey Tahiti, he wants to spend as little money as possible on reaching his utility level of 10. His cost function he faces is given by this expression, where the price for one beer is $1, the price for a pizza is $2.50. So in the following graph we then add a green structure in order to visualize this cost function. We see that we will need to take the trace of the Cobb-Douglas function when utility is equal to 10, which is the intersection of the orange plane and the blue Cobb-Douglas function, and project it onto the green plane to see where the price is minimized. So in order to actually find the minimum, we set the Cobb-Douglas utility function to 10 and find the x and y coordinates, where again the orange plane intersects the blue surface, and get this expression. Graphically, this again looks like this. Lastly, we want to get exact numerical values of x and y, so that Joe exactly knows how many pizzas and how many beers he needs to consume in order to be fully happy. We restructure our expressions and get y1 with the help of the constraint, and set x0 and y0 as starting points, namely we take 4.6 and 2.7. We also calculate the derivatives, the partial derivatives of the constraint and cost function. We then plug this into the algorithm of Newton's method, and after one iteration we get the following values, namely he should consume 4.528 beers and 2.71 or 2.72 pizzas in order to meet the utility level of 10 at the lowest possible cost. We make sure that this actually is a optimal point by calculating the ratio of the partial derivatives, namely of the constraint and the cost function, and see that they are proportional, since this value is almost very close to 0. So we see that Joe should consume 4.5 beer and 2.7 pizzas. So thank you very much for listening to our presentation, and have a great day.